In this video, we're handling an integral by using trigonometric substitution, but then the integral that results from the substitution has even powers of sine and cosine in it, and this requires that we use power-reducing identities to proceed with the trig integrals. So to begin with, the trig sub I'm trying to make is to simplify 1 minus x squared. And what I have in mind here is that 1 minus sine squared gives me cosine squared and would allow me to simplify that radical expression. So I start by saying let x equal sine theta. I also have to transform my differential. So dx is going to be cosine theta d theta. And I want to transform my limits of integration so I can forget about x after this point in the problem. When x is equal to 0, sine theta is equal to 0, and that happens when theta is equal to 0. And when x is equal to 1, sine theta is equal to 1, and that happens at theta equals pi over 2. So I have the integral from 0 to pi over 2 of x squared, that's sine squared theta. Then I have the square root of 1 minus x squared. Well, that's 1 minus sine squared theta, and there's an identity for that. It's cosine squared theta, but it's inside of a square root. So that undoes the squaring of it. And then dx is the last piece I need to tack on. That's another cosine and a d theta. So I'm left with this non-trivial trig integral. Integral from 0 to pi over 2, sine squared theta cosine squared theta d theta. Now you might think of modifying one of these terms by using that same Pythagorean identity. Sine squared is 1 minus cosine squared, or vice versa. But all that happens is you keep generating new integrals that have an even power of sine and cosine in them, and you can't get anywhere with it. So the way to make progress on these is to use the power-reducing identities. Sine theta, sine squared theta is 1/2 1 minus cosine 2 theta. And cosine squared theta is 1/2 1 plus cosine 2 theta. When I make these substitutions, I'm going to go ahead and pull a factor of 1/4 out in front of the integral. That's just both 1/2 factors multiplying each other. Integral from 0 to pi over 2 of 1 minus cosine 2 theta multiplied by 1 plus cosine 2 theta d theta. And I have to expand this thing. And fortunately, it's a difference of two squares kind of thing, because I have 1 minus in the first one, 1 plus in the second one. And my cross terms are going to cancel. So I end up with a 1 for my constant term. And then a minus cosine squared 2 theta for my last term. And again, the cross terms cancel because they just differ in sign. And now I'm still left with an even power of cosine. You might say, well, why not replace this with sine squared 2 theta? And it's fine if you want to do it that way. But it's unavoidable that you're going to have to use one of these power reducing identities one more time. So I'm just going to directly use that on cosine squared. And I end up with 1/2 times the quantity 1 plus the cosine of twice the angle, which is now 4 theta. If I distribute that negative 1/2 and combine my constants, 1 minus 1/2 is just 1/2, and then I have minus 1/2 cosine 4 theta d theta. At this point, I can guess my antiderivatives for each of those terms. I get a 1/2 theta for that constant. And then this trig piece, well, I need to have the derivative of the interior function sitting right next to it. So I'd really like to have a 4 right here. And I can get that 4 by just compensating out in front. So I have negative 1/8. That's just this piece. And then antiderivative of 4 cosine 4 theta, which is just sine 4 theta. Take the derivative of it so you can see how the chain rule works to get you back to that. And then this whole thing is evaluated from 0 to pi over 2. It's very typical in these integrals that when you're evaluating the result, things get very simple. So I want to take a big picture view of it before I start to systematically plug in the limits of integration. And the first thing I'll look at is the lower limit. When I plug in 0 for theta, that first term is 0. When I plug in 0 for theta in the sine of 4 theta, that's the sine of 0, which is 0. So both terms vanish in the lower limit. And that's out of the picture. What about the upper limit when I plug in pi over 2? Well, when I plug in pi over 2 for theta, that's not going to vanish, so I'll have to get back to that. But when I plug it in for theta in the sine of 4 theta, 4 times pi over 2, that's 2 pi, and the sine of 2 pi is 0, so that term is gone. My only survivor here is when I plug that upper limit in to the first term. And I have 1/8, that's just the 4 and 2 there, multiplied by theta, which is pi over 2. And that simplifies to pi over 16. And we're done. If you find the math content on Zach's Lab helpful, click on the Zach's Lab logo on the right to browse playlists and subscribe to the channel. I produce dozens of new videos per month, and subscribing is the easiest way to find new content. Thanks for watching.